Hey y'all. So I told you guys that I would do a Castify today to kind of show you a little bit how to compute um, the weight of an object first in metric and then of course converting that into a language we understand a little bit better in the imperial system, or in pounds as we like to say here in the good old USA. All right, so first of all, what does it mean when we're talking about weight in the metric system? So in order to understand what weight in the metric system is, we need to kind of think about what determines weight. And weight has to do with the mass of an object times the acceleration or the pull of gravity, that force of gravity pulling us to Earth. So to measure the weight here on Earth, we're going to look at something like a pumpkin. Ugh. So I got this beautiful, gorgeous pumpkin that I've never seen one quite like this at the orchard a few days ago. So this is one of the 13 pumpkins that I got. So this pumpkin is heavy. It's actually a lot heavier than it looks. So let's say this pumpkin here had a mass of 20 kilograms. Because remember, in metric system to determine force, or any system to determine force, you're going to take your mass, you're going to multiply that times acceleration. So let's say this is 20 kilograms, and let's say I dropped it. If I dropped it, it's going to fall to the earth at the rate of 9.8 meters per second, because that's the acceleration of gravity here on Earth. When an object is in free fall, in other words, when the air resistance isn't working against it yet, when it's just falling, after 1 second, it will have traversed, it'll travel 9.8 meters. After 2 seconds, it'll go 9.8 meters plus 9.8 meters per second. So it's going to go faster and faster and faster and faster until it reaches terminal velocity. Refer back to your vocabulary for that. All right, so let's look at this for a second. Here on Earth, we know that the acceleration of gravity is 9.8 meters per second per second. And we know that the mass of my pumpkin over here was 20 kilograms. So how do I determine the weight of this? Well, if you all see my calculator right here, I'm going to go 20 times 9.8, because that's 9.8 meters per second acceleration. Because remember, force is mass times acceleration, right? And force, when we're looking at weight, weight is the force that gravity is pulling on us. So to determine the weight in metric system, we use newtons. So newtons equals force times acceleration. So mass times acceleration. So I said force times acceleration, mass times acceleration. So I took my 20, because that's my 20 kilogram pumpkin, times 9.8 meters per second, because that's my acceleration of gravity here on Earth. So I would look at my pumpkin right here being 196 newtons, not 196 pounds. 196 newtons. So the weight of my pumpkin here on Earth is 196 newtons. Now, what does that mean in pounds? Well, I would divide that by 4.45, because our pumpkin, we don't walk around saying, oh, that's 197 newtons, because here in the United States, we're going to look at our pumpkin in pounds. So my pumpkin weighs about 44 pounds. Right? Yeah, that's a dense and heavy pumpkin. So why 4.45? Well, because 1 pound is equal to 4.45 newtons. So we're just converting newtons into pounds. Now, let's do an experiment. Let's say we went to Mercury, and we know that Mercury has the acceleration, because it's so much smaller than the Earth, that it's only about a third of the mass of Earth. So we know the acceleration of Mercury is only 3.6 meters per second. So if I dropped that same pumpkin on Mercury, it's going to fall more slowly because the pull of gravity isn't as strong. Now, how do I know 3.6? Well, first of all, this graph right here tells me that it's 3.6, and I also know that Mercury is about a third of the mass of Earth. So I'm going to take my pumpkin, again, still being 20 kilograms, and I'm going to multiply that now by the acceleration of gravity on Mercury, which is 3.6. So what would my pumpkin weigh on Mercury? It would only weigh 72 newtons. It would only weigh 72 newtons. Does that mean that my pumpkin suddenly got smaller? No, the mass is still the same. The mass is still 20 kilograms, but the pull of gravity is less. So the force that is pushing down on my hands as I'm holding that pumpkin is going to be less. Now, what does that mean here in the United States? Well, I'm going to take my 72 newtons and I'm going to divide that by 4.45. And I'm just converting newtons into pounds. So my pumpkin on Mercury would only weigh like 4.5 pounds. Nope, that's right. I forgot to press equals. It only weigh about 16 pounds. So it'll be about a third of the weight as it was here on Earth, because Mercury is a third approximately of the mass of Earth. You with me so far? Now, in our chart that we looked at today, you're looking at all these different planets, right? And the same mass object. In this case, our mass is 35 kilograms, which is about what my big dog weighs. Okay, it's about 70. Well, I'm going to give you an answer. It's about 76 and a half, 77 pounds on Earth. I mean, it's heavy. All right, so we're going to go ahead and look at this. So how did they do this? Well, you took the mass 35 and you multiplied that by the acceleration due to gravity on the planet Mercury. So 35 kilograms times 3.6 equals 126. And then now I want to convert my 126 newtons into pounds. I'm going to divide that by 4.45. All right. Now I'm going to go ahead and do the next couple for you. So let's look at on Venus. Now, let's say I take our dog Aquila, my big old dog, and I take Aquila up to Venus. Now, Venus is roughly the same size as Earth, a little bit smaller in mass, but I'm going to look at 35 kilograms, so I'm still going to do 35, and I'm going to multiply that by 8.9, because the pull of gravity on Venus pulls us at the rate of 8.9 meters per second per second. So that's going to be 311.5, so 311.5 newtons. Am I going to be like, oh yeah, 340 newtons? We don't usually use newtons here. So we are going to divide that by 4.45 because there's 4.45 newtons per 1 pound. So we're just converting it. And we're going to find that a kilo would weigh about 70 pounds on Venus. Now let's see about here on Earth. Well, make sure I clear my calculator. And let's look at 35 kilograms because there's still 35 kilograms. And you're going to multiply that by the pull of gravity, which is 9.8 meters per second here on Earth. And I'm going to come up with 343 newtons. 343 newtons. Now I'm going to convert that 343 newtons into pounds. So 343 divided by 4.45, because there are 4.45 newtons in every 1 pound. And my weight for Aquila is 77.0786516 pounds. We're going to round that to the nearest whole number, and I'm going to say she weighs about 77 pounds here on Earth. All right, we're going to do one more. So Mars, even though Mars is about the same volume as Earth, it's actually quite a bit less dense. So there's far less gravitational pull on Mars than there is here on Earth. So we're going to look at clearing our calculator again. We're going to look at 35 kilograms because Aquila is still going to weigh 30 or still have the mass of 35 kilograms. And up on Mars, it's only 3.8 meters per second per second. So the pull of gravity is going to be less because it's less mass. So 133 newtons. So a kilo would weigh 133 newtons on Mars. But what would she weigh in pounds? I'm just going to simply divide that by 4.45 to give us what a kilo's weight would be in pounds. Because remember, 4.45 newtons for every 1 pound. So she would have the weight, I'm going to go ahead and round that to about 30. I'm going to round that to the nearest whole number. So she would have the weight of about 30 pounds. So as you continue your chart, what you're doing basically is just multiplying your mass times acceleration to get your force. That's your newtons. And then converting your newtons into pounds by dividing it by 4.45. All right, hopefully this helped you guys out. And thanks for watching, and I will see you later. Bye.